Hello friends, in the previous video I talked about the basics of the simulation, and in this video we are going to go more in depth and learn how to have control over the acceleration and initial velocity, and also making collision function between the particles and other objects. So let's dive into it. Okay, here we are. Let's delete everything first and make a plane. Set the size to 20 and also making a torus. I want to give it more segments. And make it smaller, like, okay. Now we are going to go in geometry nodes, a new one. Distributing some points on the torus. Distribute points on the face and set it to 100. And then simulation node, which we can have access in here, simulation zone. And also want to add set position node. In here, in the previous tutorial, we used displacement vectors to move the points at each frame. So we made some displacement vectors by cross product and the noise texture and connected that to the offset of this set position node. But this time I want to have control over my accelerations and velocity. For example, if I want to have gravity, which is an acceleration, how can I make that? Let me make a vector in here. And the acceleration is a vector which is pointing toward the Earth. So it is minus 9.81 along the z-axis. And I should somehow connect this acceleration to this set position, but of course it should be converted to displacement, and then I can connect that to the offset of the set position node. So how can I do that? Let me have quick explanations in here. For example, if we have a point in here at frame 1, I should make a displacement vector and give it to this set position, and this will move this point to the new position at frame 2. And at the frame 2, the simulation, as I explained that in the previous tutorial, will go back at each frame and it will do all this stuff again. So it will make new vectors, displacement vector based on the things we defined in here, and then use that in the set position node, and it will move the point to the new position like this. And this process will be repeated at each frames. And since I know that I have an acceleration, it means that the velocity changes. Actually, acceleration is the change of the velocity in the period of time. So, for example, at frame 1, we have v1, and in here v2, v3. And we have some formulas in here. Let me show you. The delta p, which we need ultimately to give it to the set position node, is equal to v average, or average velocity, multiplied by delta time. So what is average velocity? Well, for example, when we are at the frame 1 and this displacement is happening by the average velocity between these 2 points. So the average velocity is the v1 plus v2 divided by 2 in here. Pretty simple. And the average velocity in here, when we are at the frame 2, it's v2 plus v3 divided by 2. Pretty obvious. And the delta t, well, is the delta time between each frame, which we also access in here in the simulation input. And what is delta time in here? It depends on our frame per second, FPS, which is in here. Our frame rate is 24. So it means that the delta time between each frame is 1 second divided by 24. So it's pretty small. And the second formula is the acceleration, which equals v2 minus v1 divided by delta t. Well, the v2 is the secondary velocity and the v1 is the initial velocity. For example, in here it's v2 minus v1 over delta t, but in here it's v3 minus v2 divided by delta t. So based off these two formulas, we have a formula for delta p, which is this one. And in here, the v0 is the initial velocity. Well, at each frame, pretty obvious. For example, at frame 1, the initial velocity is v1, and in here is v2, in here v3, and goes on. But we can make this formula a little bit simpler by ignoring this part. Because in here we want this formula for each frames. It means the delta t in here is the delta time between each frame, which is very small value. And especially when it gets squared, it will make it so much smaller. So this part would be negligible and we can ignore this part. And also in the further steps, it can help us to make things simpler, like when we are making collision functionality. So we can say it equals to v0 multiply delta t. Of course, if you want to be super accurate, you can consider this part included in your formula, but visually it won't have so much difference, especially in regular accelerations, unless you are using super high accelerations. But instead we are reducing the calculations so we can have little bit of optimization in this simulation. Okay, now we simply have our displacement vector, which we can connect to the set position node. And the other thing we need is the secondary velocity at each frame. The initial velocity at frame 1, we specify the initial velocity. But at the second frame, our initial velocity is our v2 in here. So in the previous frame, I should define the v2. I should specify the value of it and introduce that to the simulation node. So at each frame, we need to calculate the secondary velocity. For example, when we are here, we have the v2, which is our initial velocity, but we should also calculate the secondary velocity. And that's pretty simple based on this formula we have. This is our initial velocity at each frame, and this is what we want. So based on this one, secondary velocity is equal to a multiply delta t plus v1. Okay, that was also pretty simple. So we have two main formulas and we are going to use it in the simulation node. And we should also consider that displacement, velocity, acceleration, they are all vectors because they need to have direction in the 3D space. But delta time or delta t in here is simply a scalar value. So first I'm going to make this one the delta p. So I'm going to use a vector math node. And set it to scale. Because I want to multiply the velocity by the delta t. And here is my delta time. I'm going to use it in the scale and I need the velocity. And how can I get the velocity? Well, as we have in here, I can have my first initial velocity at frame 1 and have control over it, like the acceleration which we have in here. And it's like an attribute for each point. I can just simply connect this vector to here, and as you can see that this simulation node automatically gave me this input vector, which is my first initial value just at the frame 1. And also it gave me this input, this vector, which is the same as this one. Let me change the name of it. Can select this simulation and going to nodes, vector, I want to call it velocity. Here is also the velocity, and the velocity, and also it has an output. And as you can see in here, I can get the velocity at the first frame, which is this value. I want to keep it 0 for now. And then in here make the displacement vector, and after that I can achieve the secondary velocity by this calculation. And I will give that secondary velocity to this one. And then at the next frame I can get back that velocity value, which is my v2 from the simulation input node from here. And I can use that as my initial velocity at frame 2 and make the displacement vector from that, and also calculate the secondary velocity, which will be v3 at this frame. And it will happen again and again at each frame and goes on. Let me show you. First, I can say, okay, I have my initial velocity. I multiplied this by delta t, so I have my delta p. I can just simply connect it to the offset. Okay, and the second thing, I should calculate the secondary velocity at each frame. So I have my initial velocity, which is v1 in here, and also acceleration and delta t. So I should scale it by t and add it by v1, which is initial velocity at each frame. So I can access this initial velocity from here. And for example, in here I'm at the frame 1 and I have 0 as the initial velocity. After doing this stuff, it will give me the secondary velocity v2. So I'm going to introduce the secondary velocity to the simulation node. And at the next frame, which is frame 2, this node, this simulation zone, will give back to me the secondary velocity from the previous frame, which I plugged into here. And now I can get it from the beginning, from here at the current frame. So now at frame 2, I can have access to v2, which was the secondary velocity I calculated at the previous frame. It is also true for the third and other frames. These steps will be repeated at each frames, again and again. Okay, I have it. I should have my function. Let me take a look. I am going to hide the plane, and of course bringing the timeline. Okay, now let me play it. Okay. It's just dropping down because of the acceleration, the gravity acceleration I introduced to it. Here is when I can define initial velocity. Let me just give a little bit of velocity in the z direction, positive z direction, like 5. Okay. Now you can see what is initial velocity. It's like throwing up one object and it will fall down by gravity. And I can add some randomness to it, like noise texture. And also I want to use map range. Since the color is a vector, I should use vector map range. And the default value of noise texture is between 0 and 1. And I want random values along xy plane between, for example, -1 and 1. But I want the values along z-axis to be from 0 to, for example, let me say 5. Let me check. And connect that to the initial velocity. Okay. Let me just bring it up. Okay. Nice. Now I want to clean stuff a little bit for further steps. So I'm going to group them and select all of them. Okay, Control G. Now I should give them proper names. Simulation. This is my simulation node. Okay, in the next step I want my torus to keep producing these points and add to this simulation zone. So how can I do that? As you can see, these points are only produced at the first frame. So I want to add the same points at each frame. So I should get these points and join them to the previous points. So in here I can use all of these points and connect them to the set position. But we should know that when we define this velocity attribute for each points in here, these newly joined points, they also should have these velocity attributes. So I should add them. Well, first I can capture the attribute for these new points and set it to vector and connect this velocity, which is also connected to the simulation input. And now I should add these new attributes, or better to say new points attributes, to the previous one. As I join the points together, I should join their attributes. So I add them and I use these as my initial velocity in here. Now let me check. Okay, now in here it's producing the points at each frames and add them to the previous points. But the problem in here, as you can see, is that they are all following the same pattern, because these distributed points, they're all like having the same pattern. So I should change the pattern by changing the seed. So I can use time, scene time, and connect the frame to the seed. Now let me check. Okay. And also you can see that the noise pattern in here is constant. So you can see that they all have like a same pattern in here. And in here I want to change the pattern by the time. So I set this noise texture to 4D and it will give me the W parameter, which is like a seed, and it moves the noise texture. So I can connect the second, because it's the slower version than the frame, and connect it to the W, and let me check it again. Okay, you can see that the pattern is moving. And in here, well, you can change the noise parameters and also these range of numbers. If you want to give more contrast to the noise texture, you can change this from min to, for example, 0.2 and this from max to 0.8. It's like a color ramp. when you slide these two values and make them closer to each other, it will give you more contrast, right? And in the next step, you can look at this. It's producing the points forever. And I don't want this. It will make things heavier. So I want the points to fade and get deleted after a certain amount of time. So I should obviously delete the points by an attribute. That attribute is age. I can define an age attribute for the points by the frame. So first let me bring the delete geometry node. Okay. And also I want to define this attribute for all the points. So I can say capture attribute and set it to integer, because the age is actually the amount of past frames. And I can connect this to the simulation input and call it age. And after having this attribute, I wanna add one number during each frame. So I can have a bigger age at the end of the frame. And now in here that I have my age attribute, I can say I want to select the points for deleting the points which the age of them is higher than something. So I get the attribute and say greater than. It's a compare node, selects the points by the threshold we specify in here. So I can say, for example, 50 frame, and the result will be selected. It means that the points with the age of greater than 50 will be selected for being deleted in here. So let me check. Yeah, they are getting deleted after 50 frames. Let me reduce it. Okay. And if you want things more natural and satisfying, you can just add randomness to them. So I use random value in here, set it to integer, and set it like between 15 and 30. And I can connect this to the B input instead of having a constant value. I can have random values, you can see. You can change the number. Okay, here we are. This is how simulation is working. Let me cut it. I forgot to set it to 0, and by default this new points attribute is 0, but this one had a value inside of it. So let me connect them together, and you can see yes. And as you can see in here, we have some separated parts which is growing as they are going down. That's because when the velocity is growing, these distances also increase. So what is that? Well, that's for the inaccuracy of this simulation. This is not like a real world. If they are all just happening between the frames, and we only have 24 frames like we specified in here for each second. So if I just increase the frame rate like to 60, we should have more accurate simulation. I should change something in here. Okay. Since this is defined by the frame increased, and yeah, you can see we don't have those distances. That's because the accuracy of this simulation is increased. But the fact is that I can't just increase the frame rate for more accuracy. I want to have my original frame rate. I want to have 24. And you know what? If you have 60 frames per second, you can't have motion blur in Blender. So we need to stick with our original frame rate or any frame rate we want to have in our project. So we just can't increase the frame rate for achieving more accuracy. So in the last step, I'm going to show you how to increase the accuracy. It is like the previous tutorial somehow, which we increased the accuracy, and we are also going to do this in here, but with a little bit of difference. So this is our simulation. Okay, here it is, our simulation, and in the next step we are going to make collision functionality. Well, in the previous tutorial I talked about the collision between the particles themselves, but in this one I'm going to talk about the collision between the particles and some other surfaces. So let me explain that, and let's turn on the plane. The plane would be our collision surface, and well, when the particle is moving toward a surface like this, it should be able to bounce back. And if we consider these arrows as the velocity direction of our point, it means when it hits the surface, it should be reflected from the surface, while the angle between the velocity and the surface normal in both directions are equal. And when we are talking about the simulation in the computer, there's something important, that it is not the real world, so the points are moving among the frames. For example, at the first frame, it is the position of the point, and at the second frame, the point is here, and at the third frame, the point is here. There is no any middle positions between these 2 points. Okay, it jumps from here to here and from here to here. So you can see that as our frame rate increases, our simulation accuracy also increases. And the fact is that when they jump between the frames, there is a very small chance for this point to exactly hit the surface to bounce back. Okay, so it might be in here, or might go under the surface, or may have any kind of distance from the surface, but there is a very low chance for the point to exactly hit on the surface. So in here we should define a threshold, like a distance from the surface. When the distance between the point and our plane is less than this threshold, we can say, okay, we should reflect the velocity vector of our point to simulate bouncing back of the point. So first let me bring my plane in here, which is my collision object, and set it to relative. And first I need to get the distance between the point and my plane. So I have the position of my point by the position node, and I need to get the position of the nearest surface to my point. So I can use geometry proximity and set it to face, and I should give it the target geometry. Well, my current geometry in here, I'm working on the points, and I should get the distance of this current geometry, which is the point, to the face of my given object. So this distance is exactly what I want. And I want to say, if the distance of the point to the surface was lower than a threshold which I specify, you can reflect the velocity vector, but otherwise you can't reflect it. Let it just continue its way. So, for example, at the frame 2, the distance of the point and the surface is not less than the threshold, so it won't change the direction of the velocity and lets this point to continue its way. But in here at frame 3, when the distance is lesser than the threshold, so it will reflect the velocity vector. And for reflecting the vector, I need to also get the normal vector of the surface, of the closest face of my geometry. So I also need to go to the geometry and sample the nearest. I should connect the geometry and set it to face because I want to sample the nearest face to get its normal, and also I need to sample the index. I should also introduce the geometry to it, and I want to sample the index of the face. This node finds the nearest face of the given object and it gives the index of it. So I should plug in the index to this sample index node. And since we need to get the normal of the faces, so I should set it to vector and bring normal node and connect this to the value to sample the normal of the closest face of this object. Now time to check if distance is less than a threshold to reflect the vector. I can say the distance, if the distance is less than a value like 0.2, I can also use a switch node and set it to vector, because I want to say if this condition is true, I mean the distance is less than the threshold, I need to reflect my vector. So if this is true, I should connect this the reflected vector, but if it is false, I can connect the original vector which is not reflected, which is my velocity. I can directly connect this to here. But if the condition is true, I should reflect this vector. I can say reflect. It's a vector math node, and I can reflect it by the normal vector, the normal of the nearest surface, which I achieved from here. And I can connect this to the switch node. And I can use this vector as my velocity vector. Let me bring them back. Okay. In here, in the simulation, I just connected the velocity directly to the velocity input, but I want to connect this one instead of that velocity because I want to say you should calculate the delta p based on this vector, these conditions which I'm introducing to you. And in here we need to also add some details, like when the point is bouncing and the velocity vector is reflected like this, they lose their energy with each impact, so I should scale these reflected velocity vectors down a little bit. So I can scale it and say, for example, 0.7. And also I can tell you how to handle this number. Well, when you want the height after each bounce to be half of the previous height, instead of using 0.5 in here, which is actually 1 divided by 2, you should use 1 divided by a square root of 2, which is about 0.7. So I use 0.7 in here to have the half of the previous height. As I told you before, this threshold is because of the low accuracy of the simulation. When the simulation is less accurate, this threshold should be bigger to catch the point in the threshold range and bounce it back. So as you can see, this is a big number. 0.2 is equal to 20 centimeters. So for reducing this, we should increase our accuracy. But before that, I wanna add one more condition to this threshold. Here is my surface and here's the threshold. The point is coming down, and after hitting, at the next frame it will go to this position, okay? And it should continue its way, but as you can see, at this frame it is still in this threshold distance, so it will automatically reflect the velocity vector again, which we don't want it ever. I want this to continue its way, so this is wrong. I should make sure that this reflection only occurs when the point is moving toward the surface, not moving outward. So I can say the velocity vector of the point and the normal vector of the surface should be in the opposite directions of each other. So I can say if this is my point and this is the normal vector of the surface, the velocity vector is allowed to be in this range of directions, okay, except being exactly perpendicular. So I can say the angle between these two vectors begins from 90 degree, but not included 90 degree itself, and ends with 270 degree. So I can say the theta is between these values. And in the previous tutorial I talked about the cross product, and in this one I'm going to talk about the dot product. Well, the dot product between two vector A and B is equal to magnitude of A multiply magnitude of B and multiply cosine of theta. This dot product only gives us a simple scalar value, and as you can see, these values are the magnitude of A and B and are always positive since they are absolute numbers, and the cosine of theta is a part which only can be negative. I can say this condition is only true when the dot product of normal and velocity is negative, because the cosine of theta is always negative in this range of angles. So I can say only in the situation where the dot product of velocity vector and the normal is negative, I can reflect my velocity vector. So in here I can add the second condition. I should calculate the dot product of the V, which is here, dot product, and also the normal, which I have in here. And I should say when the dot product is negative, so means less than 0. And I should use AND in Boolean math. This is a Boolean math node, set it to AND. And I want to connect my first condition in here, and the AND option means both of the A condition and B condition should simultaneously be true to give me the true result, which is exactly what I want. So I connect this to here. Now I can make sure that I don't have this problem anymore, and also these points are only bouncing back when they hit the outside of a face, not the inside. It means that, for example, if we have a sphere or a closed object, if the point by any reason passed because of the inaccuracy couldn't bounce back the surface, it just got into the surface, I can make sure that it won't bounce when it hit the inner surface. And I don't want to fill the object with the points. I want to make sure that they will pass them. So let me check what we have done. Yeah, they are bouncing, everything is okay. Right. And let me show you something else. Let me increase the age threshold and do it again. As you can see, the points in here, after having multiple bounces, they just keep their slight movement in their own places. Let me show you again. Like they are moving in here, they are keeping their movement. See? Well, that's normal because, let me show you. These movements are like this. For example, in here, as you can see, the magnitude of velocity vector is being multiplied by 0.7 at each time of collision. So it will almost take forever to reach to exact 0. So we should make optimization in here, and we can say after a certain amount of value, the vector should be 0. For example, if the velocity vector's magnitude is less than 0.15, just don't multiply it by 0.7, or I can say just multiply it by 0, so our result will be 0. And in that situation, the points will stop that slight movement in their place, and they'll become static. So in here I can say, after scaling this, the reflected vector, I should get the length, and now I should check if the length is greater than a threshold, which I specify. I don't want to use this boolean in here, I want to use the math node. I want to set it to greater than, connect the value, and here's the threshold. Well, you can play with the threshold. At first I want to use 15, and I set it to greater than because if this is greater than the threshold, so it is okay, and the output will be 1. So I'm going to use on a scale again and connect this 1 to the scale, and it means nothing will happen. But if this vector, the length of it, is less than this threshold that I am choosing, so the scale, the output of it will be 0, and it means the scale of my reflected vector will be 0, which is exactly what I want to stop those slight movement. Now let me check it. Okay, when you see that you still have those slight movements, you should increase this threshold. They still have their movement, so I set it to 25. They still have it. Let me go for a larger number. Yeah, you can see that they all stopped moving. I accidentally made keyframe. Let me delete them, don't like that. Okay, but these values will change when you increase the accuracy of the simulation. And we will see and change these values after increasing that. So we made our collision function, and let me make them a group. So I think I got everything. Yes, now Control G. Okay, renaming these inputs. Also, I want to connect some of these to the input, like the threshold. And the bouncing scale. So you also can connect this to the input, but I don't think that's so necessary. Collision. Now in the next step we are going to add some accuracy to our simulation. Let me show you in here. Let's consider it is our point at the frame 1, and it's going to move along its displacement vector to the new position at frame 2. So if we want to add some accuracy, it means that we should know that what is happening between these two frames. I mean, we can break this step, like breaking this one step to 3 sub-steps. And it means that instead of a delta t, we should have delta time divided by 3. and also a smaller displacement vector. Instead of one big displacement vector, we should have break this down to 3 vectors. So we should have, for example, 3 vectors in here, and also 3 smaller delta times. So in here we can divide delta time. Let me first do this by 2. And also in this simulation node, if we give it the 1/3 of delta t, it will give us the 1/3 of that displacement vector. So I should repeat this step 3 times, but at first let me just do it for 2 times to check what is happening. And yeah, we are going to connect the divided delta time. And at the next step, I'm going to add another set position. And in here, since we are using 2 sub-steps, it's like dividing 1 step into 2. And this first set position node is moving the point to the half of the way, and the second one will move it to the end of the way. So in here, I should also use the collision again. Also connect that collision geometry. Also the simulation after that. And connecting the acceleration. Also delta time. Now we are going to use delta p in here. And secondary velocity to the output. Now let me check. Okay, everything is working fine with the same speed. Now let me group these 3 new nodes to make things cleaner, and Control G. Velocity input. And now that I have it, I can just copy this for having one more sub-step. Velocity output to this velocity input, and also acceleration. And delta time. And since in here we have 3 sub-steps, this was the first one, the second, and the third one. I should divide this delta time by 3 to have the same result, but more accurate. Now giving the output velocity to here. So, and you can also name this node group. Now let me check it again. Okay. Now that we increase this accuracy, we should go inside the collision and reduce some values, thresholds, like this one to 0.1, and also the main threshold, which is in here, to 0.07. And also they all should be changed in these collisions, so I can simply connect these values to the input to have control over them in here and make them some global values. Now let me check them again. Now, as you can see, I reduced this threshold. The distance between the points and the surface is a little bit lower. It was bigger in the previous setting, and now it's smaller. And as you remember, I also reduced this threshold, which was the threshold for the velocity, to scale them to absolute zero to stop those slight movements. And you can see if I just reduce this threshold, I might have some points passing the surface. So if you had such effect, you should just increase this. Okay, 0.06 is working. And yeah. And also I can check it out. They still have a little bit of those slight movements. So I keep it to like this one. And you can play with it at your projects. And yeah, I think that's it. And I should mention that there are lots of different collision systems. This one was particle collisions, there are rigid bodies, soft bodies, class simulations, and for more optimization they better to be coded and integrated into simulation nodes, so we should wait for that. But at this time we can just use this one for having some fun. And also I wanted to tell you, like in the video in the introduction, which there was motion blur. If you want the motion blur to work properly, it's better to, at the last step, use instance some points and instance some icosphere. For example, 0.01, subdivision 2, and instance. And also for EV rendering, you definitely need this. But in the cycles, it can just render the point clouds and no need to use instancing. But when I was playing with the motion blur, I found that it's not working properly. So when I used this instance on points, even in the cycles, it worked better, so much better, and motion blur was fine. And also in that one, I used motion blur with the default setting. And also you can increase the steps for more accuracy only in the EV rendering. For having motion blur and for also rendering, you make sure that you are caching your simulation, and you can also choose your directory, your baking directory in here. You can select these points and you can see that this simulation node is appeared in here, and then click on bake and bake from the start to this end specified in here. And you can also delete that bake by hitting this delete button. And I want to mention that if you want to add multiple objects as collision objects, like a monkey, you can, instead of using one object, make another collection. And put these collision objects into that collection and bring the collection into the points, like in here, and set it to relative. And as you can see, the output of this collection info is instances, so we should realize the instance to work. Now we can check. Now it's working. It's also considering this object as my collision object, and it's better to know, as the phase count of our collision object increases, the simulation slows down, so it's better to have them optimized. And of course you can connect this to this edge threshold to have more random result. As you can see in this video, in the part that the points are throwing away from the torus, in that moment they have different acceleration, and I'm gonna show you in here how it has been made. First, just let me make it simpler. Connect this to the input and hide this one. Okay. And also turn this off. Okay. As you can see, this is our geometry input, which we can use and just leave the other parts. And this is my acceleration input part, and I can connect whatever vector I want to this input in here. So I'm going to keep my gravity in here and also add something. Well, as you saw, the points are moving along the surface normal of my torus. So I should access the normal of the surface in here, and I can't do this after converting this torus to the points, right? So before this distribution, I need to capture the attribute, capture the normal attribute. And I set it to vector and face. Now I'm going to use normal. Now I can access the normal attribute of the faces before converting this to these points, like I can show you in here. So I'm going to use this normal as my acceleration, but the value, the magnitude of the normal vectors are always 1. So I should change them, I should have control over them. So I'm going to use scale and add them together, because I want to keep my gravity. Now let me show you what is happening if I increase the acceleration. You see? And you can also give it keyframes to all the values in here. So let me do this again. You can see apparently this number needs to be very big. Okay. And now you know that you can make any kind of vectors in here you want and connect that to this input as the acceleration input. And of course you can change the input velocity however you want, and of course I like to mention that you have the output of these attributes like the velocity, and you can use it, for example, you might see in different projects like the Blender demo file, which this velocity is used for giving different colors to the points by their own velocity. Since you have access to this velocity, you can store this as an attribute and use that attribute in the shader editor and connect this velocity, or just get the length of it and connect the length to this value and name an attribute and use it in the shader editor. And you know, there are lots of possibilities in here. You can do everything you want. Yeah, I think that's it. And thank you for watching. If you liked the video, please hit the like button. And I hope you all have good times. Goodbye.